We'll just wait for the recording to begin. Very good. All right, so hello and welcome to the 2020 Aspen Center for Physics Heinz R. Pagel's Physics Talks. This is an online version of the public lecture series usually offered at the center. My name is Paul Kushner. I'm a professor in the Department of Physics at the University of Toronto in Canada. If you did not receive the email of the lecture schedule or the description of tonight's lecture, you can be added to our mailing list by contacting the center. This series of talks will be live online every Thursday evening at 5:30 Aspen time or 11:30 p.m. UTC through August 20th. And the talks will be posted on YouTube the following day. So if you're new to this series in the Aspen Center for Physics, it's a real pleasure to welcome you to our virtual meeting today. I'm glad to see so many of you online. For decades, the center has served as a gathering place for the community of theoretical physics in diverse related areas. The center runs summer and winter sessions that consist of 1 to 4 week workshops that stimulate progress on leading edge topics of focus. The center invites groups of colleagues to work in a very interactive and collaborative environment. It encourages lots of interaction, exchanges of ideas, and really has stimulated progress in many areas of physics over the decades since the 60s. And all of this takes place in the wonderful, stunning area of Aspen and its surroundings. This is a really incredibly collegial environment, and I've really benefited immensely from the programs that have been offered here that I've been fortunate enough to attend. And in fact, this year, my colleagues and I were thrilled to receive the news that our proposed ACP workshop called Transport and Mixing of Tracers in Geophysics and Astrophysics was accepted for the summer 2020 session. This topic is all about how matter, materials, trace constituents, basically stuff, moves around and gets mixed up through the atmospheres of Earth and other planets, through the oceans, planetary star systems, and so on. And it would have been a great opportunity to push forward on the latest ideas of transport and mixing in fluid and turbulent systems. We're looking forward to this workshop, which was sadly canceled owing to the COVID-19 pandemic. So we hope to get a chance to run this workshop at a future date. But in the meantime, as a partial compensation, I'm happy to be able to introduce tonight's speaker, Professor Andrew Thompson of the California Institute of Technology. He'll be presenting his talk entitled In Hot Water, Our Changing Polar Oceans. Andrew is a professor of environmental science and engineering, and he's at the forefront of observational research telling us about the physics of the ocean's circulation and how it affects our global climate. His research on the movement and storage of heat and carbon inferred from observation and modeling studies is a very important part of the puzzle of understanding the state and fate of the cryosphere of our ice sheets and our sea ice as a result of anthropogenic climate change. So just to go over some logistics, we'll not interrupt Andrew during his talk, so you'll be muted. But to ask a question, we'll take questions at the end. Raise your hand by clicking the hand at the bottom of the screen. If you have a question, I'll call on you during the Q&A. We'll plan to wrap up by 6:30, including the question period. And we'd also like you to know that your video image may be included in the YouTube posting. If you don't wish to be seen, please turn your video off. Finally, we're pleased that many physicists are attending tonight, but as this is a public talk, please save your technical questions for another occasion, for example, by contacting Andrew separately. Okay, so at this point, I'd like to pass the proceedings over to Andrew, and welcome, Andrew. Normally we'd give a round of applause, so consider that done, and please go ahead.
Excellent. Okay, well, thank you very much, Paul, for that very nice introduction. It's a fantastic opportunity to be able to share some of the work we've been doing in this forum, so thank you for the organizers of the lecture series. And then perhaps most importantly, thanks to everyone tonight for sharing some of your time, especially in front of a screen with me. And I very much look forward to our conversation at the end of this presentation. So what I'm going to talk about today is looking at the ocean's role in the climate system, and in particular, as Paul said, how the ocean is influencing our polar regions, and in particular, how it's interacting with sea ice, both in the Northern Hemisphere and the Southern Hemisphere. Due to the time constraints, I'm going to sort of mostly focus on what's happening around Antarctica, which is a region that my group has worked on quite a bit. But when I give these seminars, we often talk about warming climate, and I think it's very important to be quite precise what you're talking about when you're thinking about a climate that's warming. So this is a figure I like to show. What you're seeing here on the x-axis is a time series that goes from the late 19th century up to the present. And what is seen on the y-axis here is a temperature anomaly. But what's important here is that this is an atmospheric temperature. It's a globally average atmospheric temperature. And when we talk about global warming, and in particular policy-related discussions about our climate and warming, we're often talking about atmospheric temperatures. And so you can see here over the last, say, 150 years or so, temperatures have increased by, say, roughly 1 degree Celsius, which is quite a dramatic change in Earth's history. And you can see here that there's more or less over this period a steady rise of that temperature, but there are certainly periods where temperatures have been invariable, and even times when it's decreased. You can see, for instance, from the 1940s to the 1950s. And so again, the emphasis here is on atmospheric temperatures. It's a property that's easy to measure and also influences us on our day-to-day life. But now if I want to move to the ocean, the part of the climate system that I think about a lot, I think I want to put this plot in context. So I'm going to show you a second plot here on my left. The x-axis is still time, but now we're zooming into a shorter period. So this goes from 1970 up to 2010, so a period about 4 decades. And on the y-axis, instead of temperature this time, I'm showing you it says energy, but one can think about it as heat content. And so what this plot is showing is the change in heat content in our climate system since 1970. And this plot partitions that change into different aspects of the climate system. And so now I'd like you to focus on that. You can see just down by 0 here, that very, very thin sliver there that's in a maroon or a red color. That's the change in heat content in the atmosphere that represents the warming we've seen in the atmosphere over the last 4 decades or so. And I want you to contrast that with these large wedges that are in blue, light blue and dark blue representing upper and lower ocean, which is the change in heat content in the oceans. And the important point here is that a large fraction, and if we want to be quantitative, it's over 90% of the additional heat in the climate system is actually being taken up by the oceans. And so in many ways, the ocean is a much better indicator and recorder of changes in our climate system. And now one can understand these changes for why the ocean looks so different from the atmosphere for a couple of different reasons. Water has a much higher heat capacity, so there's an exchange of heat between the atmosphere and the ocean, and it simply takes a lot more heat to warm up the ocean by 1 degree than it does, say, the atmosphere. But I think a more interesting component and what will be really important for this talk is my second bullet point there, which is that the ocean circulates. And in particular, when we think about how heat is exchanged between the atmosphere and the ocean, it happens at the surface. And what the ocean can do is it can take water that has taken up some heat from the atmosphere, carry it away from the surface into the deep ocean, and bring more water up that's often cold, and becomes an additional source or reservoir of heat that can be taken from the atmosphere into the ocean. So I'm going to talk a lot about how ocean circulation, how the ocean moves water around, and in particular how it moves heat around, why it's important for our changing climate, and especially in the poles. So let's actually have a look here of what does the ocean actually look like in terms of where the heat is and its distribution of temperature. So what you're looking at here, this is a map of the ocean. So, and I'm going to show a number of images like this. So let me just orient you. On the vertical axis, the y-axis, you have depth, and on the x-axis, you have latitude. And so you'll see a little map in the right-hand corner showing the Atlantic Ocean. And so what you can imagine you're looking at is, I always sort of say this in my lectures, imagine taking a large knife and slicing it down through the center of the Atlantic Ocean, almost like a birthday cake. And if you could open up the ocean and look inside, this is what you would see. And so a couple striking features stand out. One can see that the warmest water is at the surface over most of the ocean, and we'll talk about that a little bit. Most of the warmest waters are actually quite shallow. They're in the upper couple hundred meters. Most of the ocean is filled with relatively cold water that may be only a couple of degrees above the freezing temperature. But it's important that it is above the freezing temperature. So it is warmer than ice, for instance. And the last thing to note here is that you'll see, as you look at this distribution of heat, most of the temperature layers are flat. So the variations are more in the vertical, except for instance when you get out to the poles. And in particular, on the southern end here, down by 40 degrees south, you can see that these lines of temperature tilt. And the reason why they tilt is because the ocean is circulating. So here is sort of just a very schematic picture of what the ocean circulation looks like. Importantly, the circulation in the ocean happens at very large scales, which means it can take water from regions where the ocean may be taking up heat, say at the equator, that typically happens at low latitudes, and deliver it towards the poles. There's water moving both towards the poles, as you can see in this middle arrow here, and both away from the poles as well. And we'll talk a little bit about what that transport looks like. Now, I'll show one other plot here, because Paul specifically talked about tracers. One can look at how temperature is distributed in the ocean to understand a little bit about circulation, but we can actually use a range of different tracers. So I'm going to show you on the next figure a different tracer, which is a nutrient, phosphate. This is very different from temperature because here the properties are set near the surface due to biology. And so the properties are very different, say in the northern hemisphere and the southern hemisphere. And you can see these almost tendrils or fingers of red or these high phosphate concentrations moving down into the ocean, giving us a signature of how the ocean circulation is moving properties around. And so we look at these different tracers to help us understand ocean circulation. And that's a very fundamental way of how we study and explore the ocean. So up to this point, I've given you, with these very schematic arrows, a very, I would say, large scale or qualitative picture of what the ocean circulation looks like. And the reason why I got interested in oceanography in the first place, I was trained as a fluid dynamicist and spent a lot of time thinking about ocean or turbulence. And the ocean itself is very much a turbulent fluid. And so again, this is a very schematic picture. In my next image here, it's just a beautiful one. I love the ocean, a quite dramatic picture of what the ocean circulation looks like. So you'll see here in black some familiar looking features, which are the different continents. And then the colors you see elsewhere are a snapshot that's actually taken from a numerical model that I'll show a bit more of in just a minute, although we can do similar things from observations. It is a snapshot showing the surface speed of the ocean. And so where you see these lighter white and yellow colors is where the ocean is moving faster. Where you see these red or darker colors, it's where it's moving slower. And so what really is striking in this picture is all the structure that you see. So in particular, as you look close to some of the continental boundaries or the margins of the continents, you'll see these narrow and very intense boundary currents. Perhaps the most well-known one is off the east coast of the US, the Gulf Stream. But the other thing that is striking here is all of these coherent circular features that are similar to vortices that you'll see in lots of fluids that we refer to as ocean eddies. And these coherent structures are a very important part of how properties such as heat, nutrients, carbon, for instance, are moved about the ocean. And so, as I said, this comes from a numerical simulation that was actually developed by colleagues of mine at the Jet Propulsion Laboratory, just up the road from us here in Pasadena. And so this is a movie from that simulation. It's just an absolutely beautiful movie that I like to show in talks like this. Again, what you're looking at is the surface velocity field, or how currents are moving in the surface ocean. And these streaks you see are indicative of the strength or the intensity of these currents. And so we start off on the east coast of the US. You can see there that the Gulf Stream that was running up off the east coast of Florida and then detaching. We're going to move down the Atlantic Ocean. And again, what's really striking in this movie, again, are these coherent vortices or ocean eddies. And you can see them being shed there off the southern tip of Africa. Now, the ocean is in many ways similar to the atmosphere. And so these circular features that you see are in many ways very similar to storm systems in the atmosphere. So if you're familiar looking at a weather map, seeing high and low pressure systems moving about in the atmosphere, essentially these eddies are those same high and low pressure systems. The big difference, however, is that due to the different fluid properties of air versus water, these ocean storms, if you will, or eddies, tend to be about a factor of 10 smaller than atmospheric storms. And so when you look at a weather map and tend to see 1 or 2 storm systems sitting over North America, when we translate that to the ocean, instead of having a few eddies, we have hundreds of these eddies. And so this movie is going to conclude in just a minute by moving now southward through the Pacific Ocean, and it's going to get to a very important region, especially for this talk, at the southern tip of South America, which is the only region in the ocean where the currents of the circulation are not bounded by continents. And you'll see here coming into the screen is a region called Drake Passage, which is between the northern tip of this peninsula on Antarctica and the southern tip of South America. And so as we move out to look at this larger view of Antarctica, what you see is that there's a region surrounding Antarctica that we're going to talk about, which is dominated by these eddies or these ocean storms. Okay, so that kind of is the, sort of the first introduction of what I'm going to talk about today. And so my main goal in this talk is to provide some information on what controls the transport of heat towards Antarctica. And I think about it as sort of having 3 steps. The first is how it moves across this circumpolar current that encircles the Antarctic continent. And then we'll see 2 different regions that is how the heat interacts with bathymetric or ocean bottom topography near the Antarctic margins, which is near the continental slope, and then eventually on the continental shelf. Now, I'll show one more slide here. It just is a little bit about why this is quite important. One can see here that as that heat moves towards Antarctica, shown schematically in this red arrow, it eventually touches the ice. And so a lot of what oceanographers think about when they're thinking about the ocean's role in the climate system is how the ocean takes up heat. That's how we started. But it's also important to think about where that heat is delivered and what the sort of ultimate end game, if you will, of that heat is. And in this case, where it touches the Antarctic ice sheet. And so I won't spend a lot of time talking about the physics of ice sheets, because it's not really my area of expertise, and with the time I have. But it is important to note that the ocean's role in melting the edges of Antarctic's ice sheets have led us to a place where we are in the potential for having some of these ice sheets and ice shelves actually collapse, which have important implications for global sea level rise. And in fact, it's been argued in some of the regions that I'll talk about in the next few minutes that some of this potential for collapse may already be underway. And one of the real open questions is, what are the timescales over which some of these ice shelves might collapse? And what is the timescale at which losing some of the ice in these ice sheets might contribute to sea level rise? So, okay, so that's sort of my introduction. I'm going to do something I think somewhat brave here, is that I'm actually going to do a short fluid dynamics experiment for the moment. So I'm going to try and see if I can just stop sharing my screen here for just a moment. Okay, and hopefully everyone can now see me as a speaker. And this is an experiment I often do in my class, and it's going to be important for some of the things that I talk about here. It's a very simple question, and hopefully people can see this. Okay, I have here 2 glasses of water. Okay, I filled these glasses from my tap about a half an hour ago, so the water is exactly the same, and most importantly, they are exactly the same temperature. Okay, so now one thing I'm going to do, we know the ocean is salty, so I'm going to take one of these glasses, and I just have ordinary salt here. This is something you can do at home, and I'm going to put salt in one of these glasses here. And you can put a fair amount in, like so, and I will just stir this up a little bit. So now I have 2 glasses. Once again, both are the same temperature, but the one on my right here is salty, and the one on the left here is fresh, okay? And then what I often do, and this is kind of the fun part, my daughters in particular enjoy when I do this experiment. The night before, I went and made myself some ice cubes. These are not your ordinary ice cubes. I've colored these ice cubes blue using sort of normal food coloring, okay? And so the question for you is, I'm going to put an ice cube in each of these glasses. The simple question is, in which glass will the ice melt more rapidly? Okay, will it melt faster in the salty water, or will it melt faster in the fresh water? Again, both are exactly the same temperature, and I will put these in like so, and wash off my hands. And so this takes a couple minutes for this to start, and maybe we'll just hold this up. You can see that already this ice is starting to melt a little bit, and you can see this dye is being distributed. We're going to come back and look at this again in just a couple minutes. But again, remember, what melts faster, salty or fresh? Okay, and so let's see if I can go back to sharing my screen now, and there'll be a little bit of a distraction here as I have these glasses in front of me, but I think that will be okay. Okay, so while this is doing its experiment, the first part in our tour of the Southern Ocean and how it moves heat towards Antarctica is, as I said, this region surrounding Antarctica where we have the circumpolar current, okay? So the Southern Ocean plays a really important role in the ocean circulation system because, as I mentioned, due to this region known as Drake Passage, it's the only way that the different ocean basins are connected. So the Southern Ocean plays a really crucial role in delivering water from the Atlantic to the Pacific, into the Indian Ocean, and of course, the other way around as well. Now, because there is this pathway to develop a very strong circulation around Antarctica, the strongest current in the ocean circulation system forms as a flow that moves from west to east, or in your view here, a clockwise circulation that goes all the way around Antarctica. And this circulation is very, very strong. But of course, what we care about is how heat is moving from the low latitudes towards Antarctica, or in the north-south direction. And it's important to note that the east to west flow is about 10 times larger than the north-south flow. And again, in particular, just sort of emphasize the point I made before, that this flow is also quite turbulent. So it develops into coherent jets and eddies. What you're looking at here again is a snapshot of surface speed, where the warm colors are showing much stronger velocities, and these greens are slow velocities. And so the question is, what is the path by which that heat moves towards Antarctica? And so to understand that question, it's important to have a look at Antarctica like this. So this is a picture of what the Southern Ocean would look like if you were to drain all the water out of the Southern Ocean. And if we were to drain it, you would see that the Southern Ocean is not sort of this flat basin, but rather contains some very significant topographic or ocean bathymetric features. So what you're seeing here in color is the depth of the ocean, which bottoms out at about 5 kilometers. But you can see significant regions where these ridges, which are essentially mountain ranges, individual islands that stick up around the Southern Ocean. And I've put here for reference, typical mountain sizes. So just behind me is Mount Wilson here in Pasadena, which is about 2 kilometers high, which is pretty comparable to these different ridges you see. And even some of these large features near the continents are almost as high as Mount Kilimanjaro. And so as the ocean is flowing around Antarctica, it has to navigate or go over these major bathymetric features. And one of the things that we have learned in recent years is that this interaction of the flow with topography is very, very important for how properties are moved around the ocean. So here's a schematic picture where we see in white flow lines that are moving from west to east in the Southern Ocean. And as they reach these submarine ridges, they either have to flow around or over these ridges. And what happens in the lee, or just behind these topographic features, is that the flow becomes much more variable and begins to meander around. It's no longer just a pure east-west flow. And it is in these places where you form more of these ocean eddies, more of these vortices, and the transport in a north-south sense is much more efficient. And this has been studied in a number of different ways. I'm just going to show one example here. So this is from some work by my colleagues showing, again, a numerical model where they released millions of individual particles north of the Southern Ocean and recorded where these particles actually moved across this circumpolar current. And so what you're seeing in this image in red are all of those places that are lighting up, which is where these particles moved from north to south across the current. And all of these hotspots, if you will, are associated with major bathymetric features. And so every time the flow interacts with these large topographic features, it provides, if you will, a gateway or a doorway opening up and allowing transport of heat from north to south. And so sort of the conclusion from this is why we certainly care about the sort of global changes in heat content around Antarctica. The changes can be due to very localized processes. And one of the nice things about this is it gives us ways to sort of target these hotspots to sort of monitor how they're changing with time. Okay, so now we're going to move a little bit closer to the Antarctic margins, and I'm going to once more, just very quickly here, stop my sharing and we'll go back to our fluid experiment. So remember, your goal here was to decide in which of these two glasses the ice was going to melt more rapidly. I should have mentioned that when I ask friends and colleagues and my students which one they think, it's usually split 50-50. We can't be that interactive. So if you guessed wrong, it's not surprising, most people do. But what I'll show is that the ice cube here in the fresh water is almost completely gone, whereas I still have a decent sized ice cube here in the salty water. And the reason why the ice melted more rapidly in the fresh water can be seen just from the distribution of the dye in these two glasses. So I think you can probably see this clearly, but if I hold that up. On the left here, where that water is fresh, as that ice melted, it was cold and it would sink. And as that water sank, it would bring up warmer water from below and begin to melt that ice. In the salty glass, same thing happens. The ice starts to melt. It's cold and it would like to sink, but it is also very, very fresh. Okay, so even though it's cold, because the glass is salty, you can see that that melted water has just pooled here on the surface. And in fact, in some ways has provided a cool bath, if you will, for that ice cube. So A, you have no circulation, no water moving in this case, and you have this very, very cold water at the surface. And so the reason why I'm telling you this is on the right-hand side, you have quite a unique system where I have fresh water at the top, but I also have warmer water below. Okay, and the reason why that is relevant for the second part of my talk here is that a lot of ice melts around Antarctica. So I'm just going to move my glasses out of the way now. And we're going to talk about what happens when we get closer to the Antarctic margins. And so this is a picture that I took from a research cruise that I was on just over a year ago, just off the Antarctic Peninsula. And I'll show you that area in a minute. Just beautiful images of sea ice, ice growing on the surface of the waters around Antarctica. And what's really unique about the sea ice around Antarctica is that there are huge differences in the amount of ice that is there in winter and summer. In fact, this is a big difference from the Arctic. The Arctic is an ocean with land around it. So when the ice forms, it can't go anywhere, essentially, or can't go too far. The Southern Hemisphere is the exact opposite. You have a landmass that's surrounded by water that allows that ice, when it forms, to move far away and eventually melt back into the surface ocean. And so one can see here that there's about 6 to 7 times more ice, or 17 million square kilometers more ice in winter than there is in summer. And every year, that 17 million square kilometers of ice melts back into the surface ocean. And so what that means is you get pictures that look a lot like this. And this should look a lot like the experiment I just did. Again, this is an image where I'm showing depth on the y-axis, latitude on the x-axis. And so when you are closer to the northern part of the Southern Ocean, which is on the right, you can see that the warm water is near the surface, and then it gets progressively colder as you go down. And then at some point, as you move south, you begin to get into regions where there's a lot of melt, ice melt at the surface. And you can see this layer of very cold, fresh water at the surface that in some ways shields this warmer water that's underneath it. And so as we start thinking about how the ocean interacts with the Antarctic ice sheet, it's very important to keep in mind that that warmest water does not sit at the surface, as it does pretty much everywhere else in the ocean, but it lies at depth. It lies at a depth of about 500 meters, which is important for the types of processes that melt the ice, and of course is extremely important for how we actually observe that warm water, because we can't see it at the surface. So in the next figure I'm going to show a couple different examples of what can happen to that warm water as it approaches the Antarctic margins, and in particular, when it gets close to that region where there is what we refer to as the continental slope. So I'm going to show you 3 different pictures now that are similar to what I just showed. So it's a distribution of temperature near Antarctica. So again, the y-axis is depth, x-axis is distance, and the colors here are temperature. The color bar is on the right. And that gray region on the left there is land. So this is a region where the continental shelf is about 200 meters deep, and then it sort of slopes down, and we're seeing that warm water move towards that continental slope. Okay, so again, we see the warmest water, this red water, sits at about 500 meters depth. And in this particular region of Antarctica, that warm water crashes into the continental slope. Okay, so it does not have a path onto the shallow part of the shelf, which is where the ice sheets are. So that's one regime that we see. In other places, you can make very dense water on the shelf that essentially cascades or flows down the continental slope. And that's that thin blue line that you see sort of sitting just above the continental slope or the sea floor. And in the process of doing that, it sort of pushes up that warm water and provides it a pathway onto the shelf. And in the last example I will show, there are regions around Antarctica where that warm water flows almost unimpeded onto the continental shelf. And one thing you can see here already is there are differences in how deep the shelf is. So on the right, the shelf is about 600 meters deep, and on the left, it's 200 meters deep. And that is part of what differentiates these regions. I won't spend a lot of time going into all the details about what separates these different regimes, but it is very important for the kind of last part of this talk here to understand that there are very different regimes around Antarctica. And so that's what I'm showing on this left-hand picture here. You're looking down at a map of the Antarctic continent. And what's shown in color here is, again, temperature. This is the temperature now over the continental shelf. So that shallow region, that's about 500 meters deep and can extend for maybe 100 kilometers away from the coast. And it's temperature right at the bottom. And again, it's temperature at the bottom because usually that's where the warmest water is, not at the surface, but at the bottom. And you see strikingly that there are 2 regimes. Okay, over most of Antarctica and in the region to the right, which we refer to generally as East Antarctica, we see that the shelf is relatively cold. And in particular, that cold water provides a bit of a barrier for keeping that warm water off the shelf. Whereas in West Antarctica, and in particular in that region that is to the left or to the west of the peninsula that sticks out, you see that there's much, much warmer water on the shelf. And as we'll see in a minute, this is the place where we're seeing the most striking changes in Antarctic ice shelves. And when you look at this distribution, this is showing, again, sort of an average picture of the temperatures. We have also done some work on how these temperatures are changing. So on the right here is a sort of similar map, but now instead of a temperature, I'm showing a change in temperature with time. And what you see is that the regions that are warm are also those regions that are warming. Okay, and these values might look relatively small. This is only about a tenth or a couple tenths of a degree per decade. But we have to remember that the water here may only be a degree or 2 above the freezing temperature. And so a small change in temperature can mean a large or larger capacity to actually melt ice. And I'll show sort of this last image. This is a slightly more complicated picture, but it really brings home the importance of this ocean heat transport. I'm showing you again one more map of Antarctica. And you'll see here around the coast of Antarctica that there are certain regions that are colored. Okay, and these are regions that we refer to as ice shelves. And these are places where the ice around Antarctica, essentially under its own weight, being compressed under its own weight, is squeezed out towards the coast. And when it hits the water on the coast, it floats. And in these places where it floats, it forms a shelf, which is this really interesting system where you have ice overlying ocean, where water can circulate underneath, overlying bedrock. And these colors here are showing rates of change in the thickness of these ice shelves. And so you see, once again, the most dramatic changes are happening in West Antarctica, where we're seeing warm water on the shelf, and we're also seeing warming on the shelf. And so some of these changes are really quite dramatic, with changes of tens of meters per decade. Again, these shelves are protecting or buttressing in some ways the flow of ice off the continent, and their destabilization or their collapse would allow the land-based ice to flow into the water here. And then sort of the very last stage that I won't talk about too much here, because I'll be honest, we understand very little of it, is perhaps the most important part, right? It is, where does that warm water actually end up touching the ice? And so here's a nice schematic showing that ice shelf and what we refer to as an ocean cavity here. So you have the ice being, again, flowing out towards the coast, beginning to float, so actually lifting off the bedrock and forming this region where you have oceans circulating under ice and above the bedrock. And again, the schematic shows that that warm water is not the surface, but flows up onto the continental shelf. And really where it does most of the melting, we believe, is right at that interface between the ice, the bedrock, ocean. So that corner down in the lower left-hand side, which is often referred to as the grounding line. And the reason why we understand so little about this region is that it's an incredibly difficult place to make observations. To actually send instrumentation into these cavities is really one of the biggest challenges that remains in terms of how oceanographers measure the ocean. And so I'm showing now just one picture here. This is a very famous picture because it's one of the few sections of temperature that we actually have under an ice shelf. This is under Pine Island ice shelf. And what you're looking at here is temperature measurements collected from an autonomous vehicle, so an ocean robot known as AutoSub, that flew under this ice shelf and almost all the way into the grounding line. And so you can see here that warm water that resides near the bottom. And in particular, in that corner on the right-hand side, you can see that that warmest water is sort of right down near the bottom. That will give rise to melt and allow this colder and fresher water to sort of flow back up under the underside of the ice shelf. So I would say these are the big challenges that we have in terms of understanding the rate at which some of these ice shelves might collapse, is the really fine details of how that water touches the ice, where it touches the ice, and how rapidly it melts the ice. One can also see here the black at the bottom is showing you the bathymetry. And so even knowing what the shape of some of these cavities looks like can be very important for understanding the melt rates. So to conclude, I just kind of want to, in the last maybe just 2 minutes or so, sort of follow up on that point, which is, how are we monitoring changes around Antarctica? What are we doing to sort of understand where this ocean heat is going? And I will say there's really no substitute from actually going on ships towards the Antarctic margins, collecting somewhat simple measurements. I'm showing here a picture again from that research cruise, which was in the Bellingshausen Sea in January of 2019. The Bellingshausen is another region where we're seeing this rapid thinning of the ice shelves. And you're looking at an instrument here that's lowered over the side of the ship. And essentially what it measures is the temperature and salinity of the water. So not too different from what I showed you in those classes. But again, understanding where that warm water is very, very important. Of course, going down with ships is expensive and it's time consuming. And so we are looking at other ways of monitoring the Antarctic margins. And one tool that my group has used is a different type of autonomous vehicle known as an ocean glider. So one can see this here. It's about the size of a person. It looks a little bit like a torpedo. And what it does is it moves up and down throughout the water column, again, measuring things like temperature, salinity, and a few dissolved gases. The important thing here is these instruments don't have any propulsion. So they can change their buoyancy, or whether they're light or dense, which means that although they are powered by batteries, we can leave them out for long periods of time. So we have done deployments of these autonomous vehicles for periods of 3 to 4 months at a time, and gotten pretty good in terms of piloting them around sea ice and other things we want to keep away from at the Antarctic margins. And the last thing I say is when you're a polar oceanographer, you're quite creative in how you collect observations. And so one other tool that we have used here is marine mammals. So here's two pictures of elephant seals. You will see the one on the right here is a small sensor attached to his head that measures, again, temperature and salinity. And these seals are remarkable. They will swim for thousands of kilometers. They forage for food in sea ice in regions that are very difficult to get ships. And so the coverage that they provide has been a remarkable tool for the oceanographic community. This data is collected and freely distributed. Just to give you a sense here, that picture I showed you from the ship was a cruise that we did about a year ago where we spent a month collecting 50 vertical profiles or single dips of that instrument in the Bellingshausen Sea. And here you're seeing a map where each of those gray dots are where a seal has gone from the surface to the bottom and measured temperature and salinity. And so, many orders of magnitude more measurements. And what's shown in color here are just those places where we've detected glacial meltwater. So we can start to use these measurements to understand the pathways of where that heat is going towards the ice. Okay, so I think I'll stop there and maybe just sort of sum up what I tried to touch on today. So we talked a little bit about how large-scale changes in Southern Ocean heat transport might depend on very localized processes, and in particular where we generate these turbulent currents and ocean eddies that oftentimes have to do with interaction with bathymetric features. Any of the changes that we see at the high latitudes will intricately involve a turbulent fluid. I'm showing a picture here on the right showing that warm water moving up onto the shelf, not as a slow flow, but in spits and bursts. And in particular, how the ocean interacts with the ice will be very, very important. And if I were to suggest what our real challenges are going forward, is that any change in polar regions is inherently a real coupled process. And this is actually something that Paul has worked on quite a bit as well. And so there's a lot of interdisciplinary work that remains for us to understand how changes in the ocean, for instance, are coupled to the cryosphere, sea ice, ice sheets, and of course, coupled to the atmosphere as well. And so again, I'll just thank you again for your time, and I look forward to answering your questions. Thanks.
Andrew, thank you very much for a wonderful, clear talk, and also one that kept very nicely to the time. What I will do now is look and scan for any questions that people have. If you have a question, you can send it to me in the chat, or you can raise your hand, and I'll scan for any hands raised. I have one question in the chat, and I'll let that be the leadoff question. So it's a somewhat technical question, but I think the answer might not be so technical. So the question is, how statistically valid are the samples or the sizes given to the modelers at JPL? So I think the question is really about how does the data from the ocean get to the modelers, and how does that process work, if I can interpret the question.
Yeah, no, that's a great question. And there are a lot of different approaches to how this is done. The one that I showed is one that is constrained in some ways by the observations. And I think it's important for some of the things that we talked about here, that model will account for almost all of the observations that are available to it. But when we talk about what's available to models, oftentimes what's available is actually due to remote sensing and satellites. And so I'd say one of the biggest constraints on that particular simulation that I showed you has to do with a couple things: how we measure temperature at the ocean surface, and perhaps more importantly, how we measure variations in the sea surface height, which is very closely related to ocean currents. And so actually this is quite important, because all of those constraints that go into that model, the data as you move progressively to higher latitudes and towards the poles, and this is true in the northern hemisphere and the southern hemisphere, the amount of data to constrain those models gets much, much smaller. And so in particular, we have not had very many satellite observations of, for instance, this variations in sea surface height. at the high latitudes because the ice tends to scatter those signals in ways that are not the same as it does over most of the ocean. And in collaboration with some people at JPL, we've developed a new product that does that. The other thing is, again, that as I talked about in the lecture, if you care about how the temperature distribution or the heat in these models is constrained, again, when you get to the poles, you need measurements that are not just at the surface, but in the interior. It is, maybe I'll say one other thing there. It is interesting to note that I made the case right at the beginning of the lecture that most of the heat in the climate system, or the excess heat, has gone into the ocean. And the reason why we know that so well is that the oceanographic community has come together over the last decade or so to work on a system of autonomous observation platforms, which we refer to as Argo floats, that sample pretty broadly throughout the ocean in the upper 2,000 meters. And that, if you go back to that figure, look at it later, you'll see that the error bars have become much smaller in recent times because we have a much better handle on how much heat is in the ocean. But once again, as you get close to the poles, those floats no longer sample very well there, either because they can't come up under ice, or they have trouble sampling in shallow regions such as on the continental shelf. So that was a long answer to it. To summarize, is we are still observation poor at the high latitudes, and it absolutely impacts our ability to sort of do predictions from models.
Well, what we've learned from the new observations is really stunning. I mean, to see that time series of heat content is really impressive. Going back, going over so many decades now. Let me just see, though I've got several questions in the chat, and I did see somebody with their hand raised, but I'm not sure if they actually had a question. It was in the video. I'll go with the chat questions, and then I'll look for hands up. Okay. Do you think, okay, so here's a question about sea level rise. Do you think that large changes in sea level over the next 100 years are inevitable? Have we got past a point of no return for Antarctic ice shelves?
Excellent. That is, I think, one of the most exciting areas of research at the moment. And there are a couple different processes at play here, which have to do with abrupt changes in how the ice sheets will behave. And let me tell you that, again, I'm not an expert in the cryosphere, but the cryospheric scientists have a much greater challenge than, say, the oceanographers do. And the reason for that is, for a long time, we have known the equation that governs flow in the ocean. It's Navier-Stokes, and we are very confident that we understand the physics that govern ocean flows. And when we simulate them in a model, we're always making some sacrifices in terms of the processes that we can resolve, but we understand the underlying physics. The situation is very, very different for the ice sheets and the ice shelves. It is much more challenging to understand how the ice is going to evolve. And maybe if I give one example of that, a couple of years ago, there was a paper that came out in 2016 suggesting that we could have very significant changes in sea level rise, in particular due to an instability which gives rise to a sort of collapse of an ice shelf when it gets too steep, because it starts to melt back. This is called an ice cliff instability. And that had not previously been included in numerical models. And when it was included, we saw some pretty dramatic and in some ways disastrous suggestions of what could happen over a couple 100-year time period. And what's exciting, I think, about the scientific process is that, that was a great suggestion. It was nice to see what happens when you put that in a model. But subsequently, people have gone back and started doing some deeper work into those physical processes that would give rise to an instability of that type. And it's somewhat less clear now whether that physical process would play out. And in particular, we've not seen it happen very much at the moment. Maybe one other thing to say is I showed one slide that suggested that some of these ice shelves are going to collapse. That is due to a different type of physical process that relates more to the underlying bathymetry under the ice. And in particular, there can be situations where as the ice starts to melt, it will be a positive feedback by which it will melt more and more and more. And that's a concern, I think, that more people have that is underway in parts of West Antarctica. So in particular, Pine Island Glacier and Thwaites glaciers, which are in West Antarctica, are sitting on bathymetry that may give rise to these types of instabilities. And again, the last thing to say is, again, somehow it's still remarkable that one of the most important things that we can do these days in terms of understanding the region around Antarctica is simply measuring the bathymetry very accurately, understanding the changes in the bathymetry.
Thanks. That's a really nice answer and opened up. Actually, there were other questions along those lines, but I wanted to switch to another topic just for some diversity of topics. Brilliant and informative lecture. I agree. Thank you so very much. Dr. Thompson's information should stimulate much more discussion among us. I do have a question. I'm a veterinarian, and I'm curious regarding the effects of the sensors on the individual seals. It appears that they could get caught on debris or interfere with inter-seal contact between them. Thanks. Do you have any comments on that aspect of the research?
Yes, so thank you very much for the comment first, but I'm smiling because this is probably the most popular question I get when I show that picture of the seals. And my standard response is, when it comes to instrumenting marine mammals, us oceanographers are sort of interlopers. And the biologists were doing this years and years before the oceanographers, and all they would use were GPS sensors because they cared where these seals were foraging and how they would go about some mating, for instance. And so they were very concerned with, when they put these sensors on the seals, whether it would influence their behavior. So are they essentially biasing their experiments? And so they put a lot of effort into studying seals that were and were not instrumented, and showed that at least with their sensors, it did make a big difference. So we are pretty confident that these are not influencing them. These elephant seals, they also molt once a year. So these are temporary accessories, if you will, for the seals, that when they molt, they'll lose those sensors. And that's why the tagging programs happen pretty consistently every year.
Oh, I'm going to interject a quick question, just to follow on. So how far under the ice shelves do the marine mammals make it? I mean, can you get pretty close to the grounding line? I imagine not, but I have no idea.
Yeah, that's right. So we do not really know how far or how often they go under the ice shelf itself. Mm-hmm. If I said that in the talk, it may have been a slip. So we're particularly interested. They forage in, so they like to come up between leads in the sea ice. Right. So leads are those places where the ice split apart and there's open water. And again, these are places that are really challenging. So, one of the things that people have done with these seals that we've never been able to do before is just understand what the average surface temperature. So there's a region of the ocean we call the mixed layer, which is a sort of a well-mixed layer near the surface. We've been able to use the seals, or my colleagues have done this, to put together a climatology or an average distribution of temperature and salinity that we can do. So, but again, they go, those seals that we had worked with were tagged here at the southern tip of South America and then swam all the way down to Antarctica.
Okay, I have one more question, I think, before our time runs out. And this is a question about the oceanography. Can the speaker elaborate on how the current around Antarctica couples to currents in the north-south or meridional direction along the Atlantic and along other oceans? So the question is about how that circumpolar current is really feeding into the other oceans.
Yeah, I wonder. Maybe I can go back. So the one thing I mentioned at the beginning that is kind of a nice component of this. So in this particular picture that I showed you, which again was this, if we were to look into the ocean, remember now that because the flow of that circumpolar current is east-west, it would be moving out of the page straight at you in this picture, in the southern part of this diagram. And one of the consequences of having that very, very strong current is that, and this is getting into a little bit of the details, but it has to do with the fact that the Earth's rotation plays a very, very strong role on the circulation in the atmosphere and the ocean. And so because that's true, one of the consequences of having a strong east-west circulation in the Southern Ocean is that it takes these temperature surfaces and it tilts them. So I sort of talked about that a little bit in this schematic, but I didn't go into a lot of detail. And that's an absolutely crucial component of the Southern Ocean in the climate system, because if you look at this picture and you were to say, let's look at that where the temperature is blue, so a big chunk of that deep ocean. If you look at where does that blue water, which is about 3 to 1 degree, where did it actually touch the ocean surface? Like, where is it actually in contact with the atmosphere? The only place where that really happens is in the Southern Ocean. And what allows that cold, dense water to sort of move up towards the surface is intricately coupled with this strong east-west flow. It's a really challenging and curious part of the Southern Ocean system. And I'll be honest, I've been working on this since I was a graduate student and still learning new things about it all the time. But essentially, the Southern Ocean provides this window for the deep ocean to exchange with the atmosphere. And one can imagine that's very important for heat exchange that we talked about, but it's also critical for how the ocean takes up and stores carbon dioxide. And so in particular, if we think about how the ocean has played a role in, say, Earth's glacial, interglacial cycles, we think that big changes in how the ocean stores CO2 is needed to sort of partly explain those large swings in climate that we've seen throughout Earth's history. And again, the Southern Ocean plays a critical role there. So that's a little bit about how that east-west circulation allows a connection in the north-south sense between deeper waters to the north and surface waters at the south.
And it also highlights all the interesting questions around transport and mixing. And it's really making me excited to have our program one day if we ever get the chance, because I think there's so much that so many science and relevant kind of applied issues that your talk has raised. So with that, I think although I have a couple of more questions, and I really apologize, what I would encourage the audience to do is to contact the speaker. His description and the poster you received includes a link to Andrew's website. So I really encourage you to reach out. These are really nice questions that we're getting still. But at this point, I'd like to conclude the lecture by thanking Andrew. We have a round of virtual applause, I know, that's happening at home. And I will just also advertise the next talk in this series, which is a public lecture again. And it's called The Hubble Conundrum, a potential hint of new physics in the universe's oldest light. And this is with Colin Hill from Columbia University. So I encourage you to attend this upcoming talk and the rest of the talks in the series through August. And again, I'd like to thank Andrew, very well done, and really appreciate hearing your perspective on what's going on in the Southern Ocean and the world ocean. Thanks very much.
Thanks, Paul, and thanks again for everybody for listening.
Okay.